Thank you, Christian, for the introduction, and thank you for being here, showing interest for this topic, which I'm aware is nowadays debated, and let's say there's a lot of interest for integrating ONNX models, or better machine learning models in general, into functional mockup units. So this work started with everyday problem that we had at our unit, and first thing first. So let me say a couple of words about who we are. I work at Fondazione Bruno Kessler, which is a public institution located in Trento, in north of Italy. They're the Blue region, and I work specifically for the hydrogen technologies and resilient energy systems unit, which develops hydrogen systems from low technology readiness level, so starting from development of new materials, components, and also by validating the technologies that we are developing in our research projects through test benches. We are part of several demo projects. We are involved in many European projects about hydrogen valleys, so those ecosystems that try to put together producers, handlers, and end users of hydrogen. And specifically, I work in the modeling group. We are about 20 people working on numerical simulations, advanced engineering, and system development. So here is where the need for a tool to embed machine learning models in functional mockup units and then into system development studies rose. We do have data from test benches that we can use in our validation of system development, and we do also have data from numerical simulations that we want to use. So yes, we started this effort to develop ONNX to FMU. We live of European and national fundings. We do have collaborations with industry, and let's say that we locate in between universities and industries. But okay, now let's jump in to the topic, the main topic of this presentation. So as I said, we needed a way to exploit the data that we produce into the development of system modeling. In particular, we develop dynamic simulations based on Modelica, and we enable we needed in particular to work with reduced order models of more complex CFD models, and a need that we had was to be able to embed specifically recurrent neural networks into FMUs. We wanted to start from a Python environment, which is usually the environment where you develop machine learning models. In particular, our colleagues do that, so that was a main need, and we also knew that we could meet the many others that are using this, and we needed also compatibility with the FMI standard. So a brief list of requirements analysis. So what we wanted from this piece of software, we wanted compatibility with the FMI 2.0 and 3.0 standards without a specific focus on Modelica. So we saw it more straightforward to develop something that could enter and use the FMI standard and then enter a functional mockup unit. We started with the need to develop cost simulation because of the tool chain that we have in the development pipeline, and we are working actively to develop also the model exchange part. We had the need for time derivative of these models, which we are actively developing, and also the need to have feedback loops within our functional mockup units. The easiest possible setup, we all want that, since this is a piece of software that put together the effort of many others. We wanted to keep it as simple as possible, and then I will show you the architecture and the widest compatibility with the machine learning models. So this gives me the chance to talk about the enablers and prerequisites that enabled this project. In particular, we started from things that were already present and open source, available from the Modelic Association GitHub page, and specifically from the reference FMUs projects. We could have started also from other projects, the FMI SDK, for example. We decided to exploit reference FMUs to bootstrap our project because it made available a CMake recipe and also all the C code that was necessary to write the functions of the FMI interface. Then if we have on the one side the requirements to be compatible with FMI, on the other side we want ONNXmodels to enter functional mockup units. So ONNX is a standard for machine learning models, and it makes available a runtime library that we need to, of course, run inference from the models in C. So we were able to find, I think, the most a very easy software, a very easy language setup based on C. So the only prerequisites we have is to have a Python 3.10 and then a C compiler. So the results. So the first approach with this tool is, of course, the mapping of an ONNX model to the FMU input-output. This is an example of a very simple graph-based model expressed in ONNX. So here you don't see the very common multi-layer perceptron. We can do many other types of graph-based calculations with ONNX, and here we simply show the addition subtraction of some scalars and then their concatenation into arrays. This means that we need to be to have availability of n-dimensional arrays, and we wanted also to be able to retrieve from the ONNX model the different heads that we have for input and output of data. So in this model, in this simple model, we have 3 inputs and 1 output. Then we have n inputs and m outputs as from our needs. To map this model to the XML model description of FMI, we opted for a very simple approach based on declaration of a JSON mapping of inputs and outputs. We have a first section where we declare the name of the model, a short description, and the type of the FMI version that we want. In this section, we may also specify all the capability flags that we want to enable or disable in an FMU, according that we know what we are doing. Then we have other keywords that are needed for mapping inputs and outputs. I do the example with the inputs. So we have this list of inputs which are characterized by this schema. So the schema includes the name, the description of the input, and this input maps the ONNX head input to the XML description. We have the possibility to provide labels and starting values for these for each of the inputs. If the input is an array, then we need to specify starting points and labels for each of the entries of the array. This can be done automatically in my mind in I don't know, in a Jupyter notebook. When you generate, you train your model, then you want to generate the FMU after you generated the ONNX model, and here you have the possibility to automatically specify all these things. And of course, then we want to go into the XML model description. The second thing we wanted was to have feedback loops, so the possibility to feed recurrent models using their outputs to feed it to the next time step. And here we bring the example of the recurrent neural network. Let's assume that we have an input array that collects a history of states and controls with which we want to feed the ONNX model, and this produces an output. So here we are simply talking about the machine learning model. We didn't talk about the FMU yet. So we have this list of things which has to be normalized. We need to do operations, and we can do all this within the ONNX model. Then we need to encapsulate this into the FMU, and to keep things simple, the things that we want to provide at each time step to this model is simply the new vector with the controls for the model, and we want to receive the prediction for the state at the next time step. So since ONNX models are somehow stateless, they cannot update their parameters during inference, we needed a local memory within the FMU. So we realized this thing by mapping the output nodes of the network to the input nodes. How we do this? When we declare the model, we do have, let's say, this type of model with three input nodes and 3 output nodes. We are able to exploit ONNX capabilities to do concatenation, squeezing, slicing of the arrays, and in this way we can provide X, which is a history of states, which is located, stored, memorized within the FMU. The thing that we provide from the FMU is U, and we also have within the FMU a history of states in capital U. We do all the stuff that the model has to do, and we return 3 different outputs. One of them is y last, which goes as an output to the FMU, whereas the others are feedback looped into the again into the model at the next time step. So we simply did this by mapping using the same names of the ONNX model, name in and name out with the description, and that enabled writing some code to do this mapping. Here I want to show you what is the architecture, so the how we do this. We start from the ONNX model on the one side and a model description in a JSON format. Then within the Python program that we wrote, we use Jinja. Jinja is a templating engine which is able to fill those parts of the code that you find within the curly braces. So I think the main contribution of this project from a scientific point of view is to write these templates that we can then flexibly fill with the things that we need to create the C code and the XML code, then to generate the binaries of the FMUs. At the next time step, we find the generation of the source code, which is done via a CMake recipe, and we can break the process of generating an FMU into 2 steps. The first one is generation of the C code and XML code, and then the compilation of the FMU, which is done via, let's say, you can interact with ONNX-to-FMU via Python and via the command line interface. So these are the 2 options that we developed in order to develop this generation process. And finally, we were able to test this toolchain using FMPy for validation and testing. So let's jump for the last part of this presentation into a real-world example that we developed, which was the development of a reduced order model of a gasification process to produce hydrogen. So what we wanted was to embed this machine learning model into a dynamic simulation that is then run in Modelon. And okay, very briefly, the gasification process includes different stages. So let's say that this is part of the gasifier chamber. We have a melting zone where we input some solid material, then some methane. We have production of solid output. Then there is a stabilization zone where many chemical reactions occur and where we inject some other gases for stabilization. And finally, we have the byproduct, the syngas of the process, which we are interested in. You see, we are interested to control the amount of hydrogen that we produce. We start from a PDE-based simulation to generate data. So we have many equations involved in the model: heat and mass balance, particles and momentum balance, melting phenomena, and the dimension of this process was a single dimension. So we modeled the vertical axis of the gasifier. And as many of you know, we have a lot of information in this model that we don't use then to run the control part of the dynamic simulation. So we were interested specifically into predicting some of the outputs. Each of the simulations to run the simulation lasted for 1,500 seconds and took almost 10 hours for a total training time of 800 hours. And we couldn't afford to have such kind of a complex model into the dynamic simulation. So we wanted to be able to predict the state of this system, molar fractions, so temperatures, pressure drops, and we wanted also to be able to inject some controls into the FMU, like the ratios that characterize the solid inlet and the flows, the inlet flows of gasifying agents and solid parts. This is very briefly what the model was doing, the machine learning model was doing. So here you can see a test example where the prediction and the truth are almost overlapped. Maybe there's some in the pressure drop plot, you can see that there is a small difference, so the model does some small error, and we wanted to be able to read these things as outputs. In this next to last slide, I present you the balance of plant of the simulation in Modelon, which had some requisites. So being a co-simulation FMU written in according to the FMI2 standard, generated in Ubuntu 20 modeling environment. We had all the labels to identify inputs and outputs of our FMU, provided from the user description. And then in this case, we do not have derivatives available, which gives me the access to talk about the limitations of this approach that we have adopted now. So first limitation might be the size of this FMU. Since we bring with us all the ONNX runtime, the size of the FMU is quite important, so 70 megabytes, and we would like to reduce this size, and then provide the derivatives and complete the model exchange integration, which is maybe the most important thing we want to do now. Then other ideas could be to benchmark the speed of this model compared to other solutions to embed ONNX models both commercially and open source, to compile, to test the compliance of this FMU with multiple instantiations, and to enhance the suite with extended testing of larger models. So thank you for your attention, and I leave you with some questions or curiosities if there are any.